All right, welcome back. Let's continue our discussion of the Chatlier's principle by talking about some of the math. We can't avoid it forever. So what we do is we compare Q and the equilibrium constant. Remember, Q is the reaction quotient. The equilibrium constant is the equilibrium constant. They're calculated the exact same way, but the equilibrium constant is only calculated at equilibrium. The reaction quotient can be calculated at any time. So we'll start by looking at that first example I showed you with acetic acid, vinegar. Now I showed you the equilibrium position of the acetic acid with 1 molar vinegar and 0.0042 molar H plus and 0.0042 molar acetate. The reason for that is because 0.0042 times 0.0042 divided by 1 is equal to 1.8 times 10 to the negative fifth. And that's the equilibrium constant for the dissociation of acetic acid. So that is the equilibrium position. So now moving forward, following the same example, we go ahead and we remove all the acetate ions using, say, silver nitrate. And this leaves us with a non-equilibrium position, with Q equals 0.0042 times 0 divided by 1 is equal to 0. That's not the equilibrium constant. That's less than the equilibrium constant. So that means that the reaction is going to have to move. It's going to have to change some things to try and get back to equilibrium. It's going to need to produce more of the acetate ion, and the only way it can do that is by dissociating more of the acetic acid. So it's going to produce more of the H plus, the hydronium, as well. So what we're going to need to do is we're going to need to plug this into the equilibrium constant expression. KEQ equals 1.8 times 10 to the negative fifth is equal to 0.0042 plus x times x divided by 1. X in this case is the amount of each of the products that will be produced when the equilibrium moves to the right. Okay, so you're going to produce x moles or x molarity of the acetate anion. You're also going to produce x molar of the H plus. There's already some H plus in there, so you add it to what's already there. There's no acetate left over, so you add that to 0. You don't really need to show that. Technically, you could also write 1 minus x on the bottom, because you are going to be removing some of the acetic acid in order to do this. But the fact of the matter is that x is going to be a very, very small number, so you ignore it. You consider it negligible. It's too small to make a difference. It'll be rounded out. You won't see it. And when you solve for x, you have to use the quadratic equation, negative b plus or minus the square root of b squared minus 4ac all over 2a, and so on. Now, what you find is that x is equal to 0.0026. And when you add that in, and you can double check the math, 0.0068 times 0.0026 divided by 1.0 is 1.8 times 10 to the negative fifth. And that's where I got the numbers for the end of that problem. And what this boils down to is that if I give you numbers instead of a qualitative sort of problem, or a qualitative problem, you should be able to figure out how the reaction is going to move. If I give you actual numbers, then you can give me the equilibrium position. And don't worry, I'll be going into more detail onto how you find the equilibrium position. But if Q is less than K, that's the same thing as saying that you've added some reactant or removed some product. Because, it's products divided by reactants. If Q is less than K, that means the top is too small or the bottom is too big. If the top is too small, you don't have enough product. If the bottom is too big, you have too much reactants. So you've added reactants or you've removed products. And the reaction will shift by removing reactants and adding more products. It doesn't have the options that you have. It doesn't have any ability to select for that. It has to do everything all at once. And it will shift to the right, is what we say there. Conversely, if Q is greater than K, that means that you have too much products or not enough reactants, or maybe both. You've added some of one, removed some. And it's going to have to remove remove products to create reactants. It'll have to do both. And that's when we say that the reaction has shifted to the left. That doesn't settle matters for what we can do with equilibrium positions, not by a long shot. Let's go ahead and move on to discussing how temperature changes, I should say, interact with the equilibrium position. So, unlike what I talked about before, temperature is going to depend upon the individual reaction. When talking about removing reactants or adding products, you could generalize it to any sort of reaction, because every reaction has reactants and products. But when you're talking about temperature, you have to consider endothermic versus exothermic reactions. Because when you increase the temperature, you're adding heat to the system. When you decrease the temperature, you're removing heat from the system. And so, if you look at heat as being either a reactant or a product, then it works. But whether it's a reactant or a product depends on whether the reaction is exothermic or endothermic. So an exothermic reaction releases energy. It heats up the surroundings. So heat is a product. Okay? So if you increase temperature, the reaction is going to respond by trying to remove heat. It's going to try to undo the change you've done, and it'll shift to the left. If you decrease the temperature, okay, you've removed heat, it's going to try and undo the change you've made by shifting to the right, exactly as it would for any other product. Whereas if it's endothermic, it removes heat from the surroundings. It's treating heat as a reactant. So if you add heat to the system, if you increase temperature, it's going to react as if you've added a reactant, and it's going to shift to the right. If you decrease the temperature, if you remove heat, it's going to respond as if you removed a reactant, and it's going to shift to the left. So you can treat temperature as if it were a reactant or a product, but you have to know whether the reaction is endothermic or exothermic. You can't just know how the system is going to respond. You have to know that fact. Or conversely, you could use that fact to determine whether a reaction is endothermic or exothermic. I never really thought of it that way before. You let the system reach equilibrium, you increase the temperature, and see which way it moves. That's interesting. All right. Another thing you can consider is pressure. I apologize for not making a slide for this, Shantia, but I didn't think about it at the time I was making these slides, and I don't feel like adding one later. But we can still consider the Chatlier and how a system will respond to a change in pressure. Now, the important thing to know here is that an equilibrium will only respond to a pressure change if there is a gas involved in the equilibrium. If there are no gases, then the system just won't respond to a change in pressure. Gases and liquids, their response to changes in pressure are so minimal that it just doesn't matter. We don't consider that. It's negligible. It's of no importance. So instead, we just look at gases when it comes to pressure. Now, in this case, it's even less determinate than with temperature changes, because you can't even consider exothermic versus endothermic. Instead, you consider the number of moles of gas on either side of the equation. Because if you increase the pressure, okay, if that's how you perturb the system, if that's the change you make, then it's going to respond by trying to decrease the pressure. And the only way it can do that is by minimizing the amount of gas. It doesn't have control over the volume of the container. The reaction doesn't have control over the temperature. So instead, it's just going to worry about the number of moles of gas. It'll respond to an increase in pressure by decreasing the moles of gas. On the other hand, if you increase the pressure, decrease the pressure, then its only response is to increase the moles of gas. Okay? And I'll go ahead and illustrate this with my go-to gas equilibrium, the Haber process, whereby ammonia is made by combining nitrogen and hydrogen. So the balanced equation is 1 mole of nitrogen combines with 3 moles of hydrogen to produce 2 moles of ammonia. And this is an equilibrium. And when you look at it, remember that the system doesn't care what kind of moles of gas you're talking about. All it cares about is the numbers. So we have 4 moles of gas on the left. We have 2 moles of gas on the right. So up top here, if you increase pressure, it's going to decrease the number of moles of gas, so the system will shift to the right. And down at the bottom, if you decrease the pressure on the system, it's going to try to increase the number of moles of gas, so it's going to shift to the left. Now, like I said before, this depends entirely on what kind of reaction you're looking at. So definitely do not try to memorize, increase pressure means shift right. No, okay? Increase in pressure means shift toward fewer moles. Decrease in pressure means shift toward more moles. So if we had a different reaction, one that had fewer moles of gas on the left and more moles of gas on the right, you would get different answers. Okay? You would shift to the right where the other one would shift to the left. And if you have a reaction where you have an equal number of moles on either side of the double-headed arrow, you're going to get no change whatsoever in response to pressure. Okay, the system can't do anything to try and undo what you've done, so it's just going to do nothing. Okay, so Le Chatelier's response to a change in pressure depends entirely upon the balanced chemical equation. And that's all we're going to do for the qualitative understanding. And it's been about 15 minutes, a little over maybe. No, a little bit under. But still, it's been about 15 minutes. So we're going to go ahead and call it a day for this lecture. And when we come back, we will look at more math. We'll look at how you can find the equilibrium position with a handy-dandy table.